Hello. So starting about independence test, there is this state-of-art HSIC, Hilbert-Schmidt information criterion, and talk more about HCR, hierarchical correction and reconstruction as replacement with improvements and other applications. So why it's easy to check the correlation of two samples. Yeah. So here is correlation. So those are very correlated. Those are very anti-correlated. But correlation for those says zero. So correlation is not sufficient to describe dependencies. So the question is how to describe, to see there are dependencies, evaluate them, and also like here, real data. So the best evaluation is in information theory is mutual information, literally saying how many bits of information one variable says about second variable. So in information theory, it used to send information that we write X, it is deformed into Y, and based on this mutual information between them, this number of bits per symbol we can transfer to such channel. So it is also, mutual information is also independent on the permutations of variables. Also, we would apply some monotonous function. It will not change the mutual information. So it is the best, consider the safest evaluation of dependence. So the best would be having evaluation of mutual information. However, for HSIC, it is both costly, this multiplication of matrices of size n by n, where n is the size of the sample. So for million, it is huge cost. So it does not provide mutual information. It's something like that, but not exactly. So in HCR, we have much cheaper. So this will be linear with the sample size and also the size of the basis. So this basis contains correlation. So one of many types of dependencies is correlation, but we have many others. So here we automatically choose a large number of them and test if there are from independent variables. So assume hypothesis there are independent and find the probability of this hypothesis. So it is much cheaper in practice. In simple benchmark show it's more sensitive to dependencies, can find more subset dependencies. It can, moreover, can describe dependencies. So not only just show if what is the strength, but also show where they are. Yeah. So by moments, by reconstruction of chain distribution from them. So it is literally finding many moments like correlation, one is basis, and for independence test, check if normalized there are from this standard Gaussian distribution. And further we can apply it for mutual information estimation. So there's getting this simple formula, all non-trivial moments between the two variables squared give approximation of mutual information. So it's very simple formula and practical. And so we have both evaluation and description, and talk about it. And I will also talk about other applications like information bottleneck for neural network training. Okay, so here is for HSIC uses this reproducing kernel Hilbert-Schmidt approach, that we have this operator which takes value of function, but in practice it's usually used for with Gaussian kernels. So in every point we put a Gaussian and getting this kind of density models. Yeah, so from these points we put Gaussian in every point, and we get these densities depending on the width, the radius of this kernel. Yeah, so the big question is how to choose it, and it's a very difficult question. There are some heuristics, but I don't think they are optimal. So anyway, we have this file which replaces our sampler with this smoothed sampler with this kernel like Gaussian. So and the HSIC is at least approximately is the cross covariance in this tensor product. Yeah, so we have one sampler smoothed with kernel with Gaussian kernel. We subtract the mean, also the second. So we literally have this kind of plots, but abstract, and find the correlation in this space of densities. Yeah, it's crucial that if we have the product of two Gaussians shifted, then it's just again Gaussian. Yeah, so we can easily get this for single points with Gaussian. We can easily get this distance with this kind of between them. So this way we have so here is this main term in norm of this cross covariance matrix Hilbert-Schmidt norm. So we can see that we get these two kernels like here, and so we get this main term in the formula, which finally this HSIC formula can be written as just this multiplication of matrices. Yeah, so K is the x to minus matrix of distances in our data set. Also, and H is this identity minus 1 over n. So it's just for the subtraction of this mean. So this is some additional. But the question we get is relatively looking simple formula. However, this is very expensive formula. Yeah, so each K and L, these are n by n matrices. Their product is like n to power 3, or the best are going to have this exponent. So this is very costly to calculate. We cannot work like if sample of million is problematic here. Yeah. Okay, so but because assuming that we get this, we calculated this formula and get this HSIC, the question is what does it give? So this is something different than mutual information. This is literally cross covariance, also the Hilbert-Schmidt norm. So it is used, for example, for neural network training. It is used as a replacement maybe for mutual information, because there are not many good methods to calculate it. This is a very basic problem, how to estimate mutual information, but not very few methods. So, but the basic application is independence hypothesis test. Yeah, so to check if the two samples are independent or not. So for this purpose, we assume zero hypothesis as they are independent. So we assume that they are independent, and they show that assuming in this assumption, they should be from a gamma distribution. Yeah, so and we can estimate that this is parameter from data. So we need to just draw this Gaussian distribution and calculate this probability that our value is larger than the observed. So this integral over this density over the tail, and we get the probability that this hypothesis is true or not. Yeah, so we can check what is the probability that given sample is independent from this test. Yes, I will show benchmark later, but generally, as mentioned, this is very extremely costly, especially this matrix multiplication. Also in HCR, we have linear times the number of moments we are considering. So it will be real mutual information approximation, at least, not exactly, but and in benchmarks, at least some simple benchmarks, it's more sensitive, can find dependencies when they are weaker and point them. It provides description, describe the dependencies. Okay, so there is also so-called distance correlation, so which looks quite similar to HSIC, but it's cheaper, so it does not use multiplication, but directly calculates the distances, normalize them, and then find the covariance. Yeah, so maybe it's quite. I don't know what's the performance, but it can be kind of simplified HSIC maybe. So it finds some dependencies here. Okay, now let me go to this HCR methodology. This is a large family of methods I'm developing for many years. So generally, this is kind of the world of methods between classical statistics, where we work on moments, we have interpretability, that we calculate them, estimate them independently. They are unique. We have some accuracy control, but they provide only very rough description, and it's difficult to find the density they represent. From the other side, we have this machine learning neural networks. They have they offer a very accurate description with huge parameterizations, but the estimation is through iteration. the interpretability is usually poor, so people don't trust, especially the finance data, don't trust them. So and there are some dependencies not unique. So the question is, could we get something in between? So what connects advantages of both worlds? And yes, we can. So like some classical statistics, we can work on moments, but special moments. So chosen such that they allow to recreate the model of probability density. So if assuming that the density is just a linear combination, in practice, preferably in orthonormal basis, for example, polynomials, then the estimation turns out, mean square error estimation turns out just average over sample of given function, like polynomial. So this way we get moments. Yeah, so we get some kind of special moments which directly give them density and have practically all the advantages of some classical approach, but allow for very large models. The number of moments for multiple variables can be huge. So this is kind of intermediate world. There are lots of applications. Okay, so let's look at simple situations. So for assuming we have two variables from uniform distribution. So if they are independent, the joint distribution is also uniform. But usually there are some dependencies, and here we describe them by contributions to density of the orthonormal family. So this one, we can see that going left, right, the expected value of second variable goes up, down. Yeah, so this is literally variance, expected value dependence, like correlation, and turns out it's very close to correlation. Then we have one, two that going left, right, the variance now grows. So this is in first and second moment. This is the opposite, and this is called homoscedasticity between the variances. So that if one stock has large change, then others probably also have a large variance. Yeah. So here are some articles I have written, prepared to this year. So lots of applications from finance, some data analysis, EEG data. Now neural networks I also mentioned. Okay, so maybe let me show some applications. Very briefly, so here is this example, one-dimensional example. So we have the points, and we like to model the density. So here is without just normalization. Here is adding the expected value, the first moment, adding variance, skewness, and so on. So we could go further. The big question is where to stop. If we go too far, in infinity, we'll get Dirac deltas. But in practice, usually fourth moment is the best for financial the data. People only consider up to kurtosis, so going up, you get noise, you get overfitting usually. So usually the basic heuristic is to go to fourth moment. And so with very high, you see that there is a problem that sometimes the density goes below zero. This is a density cannot do it, so we can, for example, calibrate it that take the maximum of this density, but then we need to normalize to integrate one again. Yeah, so this is inconvenience, especially this normalization. For neural network, we can avoid it, I think. Okay, so very briefly, there's the derivation. So we take the sampler as so G epsilon is move and a sampler with kind of density estimation with epsilon. Here is our, let's say, polynomial linear combination. So we would like to optimize its parameters. So we take this minimum. So it turns out we should go to epsilon to zero. This term goes to infinity then, but you can skip it. So doing so, and for assuming orthonormality, then we get this very simple estimation that the given parameter is just average over sample of its value function. So here is example in 2-dimension. So it's very convenient to normalize each variable to nearly uniform by going through this cumulative distribution function, like here for Gaussian. This way we get nearly quantiles. Yeah, so one half becomes the median and so on. So this is very nice normalization, which helps behavior, especially with the low degree polynomials, which are better for generalization. So I usually start with this normalization. Then we need to, as shown, we can use here is zero approximation, just uniform distribution. Then we can add this for moments. Then we can use higher. The question is how to stop. So let's go to this question. Yes, also where to stop. So here are two approaches for these points. So here is this curiosity estimation I have previously shown for various widths, and here are polynomials of various degree now. Yeah, so the question is which is the best, and to evaluate it, first of all we should use cross validation. Yes, to separate the training and test set. Yeah, so we got training set and then test on the separate set, how well the model works outside. So and we should there is usually used log likelihood so for example for average logarithm of density over our sample. So for this case this is 0. So this is log likelihood is 0 here. So here we can see that in cross validation for separate training and test set, curiosity estimation barely goes above this baseline 0. While polynomials easily can go higher and also cosines. And we can see that the best is to choose degree 4 polynomial here. Yeah, so as mentioned, usually the best is degree 4. That means considering moments up to kurtosis, then we can see there is overfitting. Yeah, so here is this best one. So and why it's better? So curiosity estimation assumes that the new points will be close to the old points. Yeah, so this is not very good for generalization. Yeah, so we have some training set here, and then the test sets will be close, so not necessary. So instead, for generalization, the moments are much better. They are literally general behavior of our data of our sample. Yeah, so we can see that for generalization, yes, the polynomials, the global basis, yes, so that work much better than curiosity estimation, which is very poor for generalization higher than one dimension. Okay, so let's look at this basis. So and also the name, the hierarchical correlation and the construction. So to justify it. So for one variable, we have this basis. Yeah, so there is 0 normalization. Then we add the succeeding moments. Yeah, so here's one variable. Then for two variables, again, we have normalization here. Here we describe this marginal distribution of one variable, here marginal distribution of second variable. And here are the dependencies. Yeah, so here is this correlation, here is homoscedasticity, and so on. So for dependencies between the variables, only those in central are crucial with non-zero indexes. Yeah, so and indeed the mutual information estimation is sum of square of these coefficients. Yeah, so very, very simple formula. So here is for two variables. For three, here we have normalization first, so 1. Then we get a marginal distribution of the first, second, and third variable. So there is 0 for the remaining variables. Then we get pairwise dependencies between first and second, second and third, first and third. Yes, and then we can also add higher dependencies, like triple-wise, that if we move two variables, the third one goes up or down. Yeah, so this kind of, so much more complicated. So we have literally this hierarchical correlation construction. We can ask for the succeeding order of dependencies and include them or not in our model. So the problem is that the number grows exponentially with the dimension, but we can restrict it to, let's say, pairwise, we get only square of the dimension, triple-wise, the third power, and so on. Yes, this is a big question. Generally, cross-validation should be used, separating the training and test set to choose it. Here is some example in high dimension. So again, we have this basis, orthogonal basis, usually as product basis, just. And the estimations, the basic estimation is very, very simple. Yeah, so and for high dimension like 9, here is this index has zeros. Zeros means that there is no dependence. And in practice, there is also it describes dependence between the second moment of this variable and second moment of this variable. Yeah, so and so some other possibilities is that it's very nice for missing data. That if there are missing some. So, for example, here, if there are missing the positions with zeros, then there is no problem because estimation of this parameter only in these two positions. Yeah, so there is missing it, the rest we can still use it for to improve estimation of given parameter. So we can optimally use the data, including the missing, with this approach. Also, I have mentioned the static estimation, but you can also use evolving estimation. So just replace average with expression with average. Now we have literally not one density, but it evolves in time, and we can look at its evolution. Okay, so now let's go to this mutual information estimation. So for this purpose, we need this approximation that logarithm of 1 plus density equals density. Yeah, so we cut the higher order, so maybe they should be included somehow, but it's not so easy this way. So doing this using this approximation, the density as integral over the cube becomes much simpler, and we get this formula with just sum of square. Yeah, so the entropy is minus sum of square of those parameters for one variable, for those parameters of the second variable. And going further, you can find the mutual information like here, and we get those non-trivial moments between them. Yeah, so the correlation, the homoscedasticity, and so on. So those are the crucial parameters we should check to look for dependencies between our two variables. So it is very similar to Wikipedia article for mutual information. Yeah, so they have entropy of one variable, entropy of second variable, of both, but some is mutual. So there is mutual information, and here we have very similar diagram. So now for HCR we also need to add estimation of the parameter. So if we write the matrix as just all the bases and for all the data set, as we have this matrix, then the estimation is just average. So one, if you multiply two, then you get 1 over n, and the product. So we get this very simple matrix product is our estimation of all the parameters. Yeah. So this matrix product estimates all, let's say, 16 parameters here, and now we can multiply it like here, and we get the mutual information for the squares. So we could use the Frobenius manner, but we can multiply it. And with the multiplication, you can see it as the kernel representation, where it becomes simpler. But we don't have to do it, because this kernel representation is costly. It needs matrix multiplication, which is very costly. Here we can instead just calculate this, let's say, 16 moments and work on them. And calculation of each is linear with the size of data set. Okay, so here is some again this plot. There are some HSIC is local based on Gaussian, which is terrible generalization, while HCR is global, so it's much better than generalization. So it should have better behavior if we build independent test mutual information estimation from them. So the better generalization is because connectivity estimation says that new points will be equal to the old points, while HCR just finds moment, which are better than describe general behavior of the data. So in kernel approach, we have these kernels, for example, Gaussians, but it's very costly. We need there is this, it's local. The question is how to choose this width of this Gaussian. It's not approximation of mutual information, so it's something strange. We don't know how to interpret it. So in HCR, we can calculate these matrices and then represent it as very similarly to kernel approach by defining these kernels as these products. So also n by n. We could do it, but it would increase the cost of calculation. We need to multiply these matrices, but we can avoid it by just working on the features. So it has better generalization because of being global. It's much cheaper. It can work on moments. It's real approximation mutual information. Also provides description. I will see in a moment. So not only how strong are dependencies, but how do they look like? Yeah. So we can now find this kernel. So for Gaussian, it would be like here. So it is infinite basis. Yes, it's Gaussian in every point of real numbers. Why for HCR we have final basis? It allows this optimization of the cost, yes, to linear with the sample size. So if we calculate this kernel, so here is the positive part. So here is everything is positive for KD HCIC. For HCR, the positive for larger degrees is literally diagonal. So it's slightly better. It's only positive than they are negative. So here we can have this kernel we can use in kernel methods. So let's now make a real practical independence test. Yeah. So so it's difficult to make a really controlled test, but here's a simpler way to do it. So we generate independence variables. So two binomial distributions left and right. So here they are independent. And now we introduce dependence by slowly rotating it by 1, 2, 3, 4, or 5 degrees. Yeah. So the question is, can the method distinguish the independent from the more and more dependent points? Yeah. So in HCR, we would literally normalize and then model the joint density as polynomial. So getting like here the color, so we can see that something's changing. Yeah. So here is some dependence described here. So, but the big question is how to distinguish noise from the signal. Yeah. So here there is also some signal here, but how to say that this is just noise, this is a rich signal. So here are the 16 moments 4x4 as mentioned. And now we'd like to perform the independence test, so hypothesis testing. So so we can normalize these moments such that, assuming independent, they would be from N01. Yeah, so normalized Gaussian in the center with 1. So and then we can test if let's say 16 moments are from normal distribution N01. Yeah, so we could use standard methods like this Shapiro-Wulff, Anderson-Darling, but they were not very good. Much better was just testing the smallest and the largest value I found. Yeah, so we just take a look at the smallest and the largest, also the most purple and the bluest. Yeah, so there are so if there is dependence, then it's probably some direction, and you can find this direction as the largest, the smallest. So and now we can compare it. What would be the probability distribution of the smallest of 16 and 01 variables? So assuming independence, so we get this plot, the blue one, and then for smallest, and then the orange for largest, and we can calculate the probability of by integrating this area. So the probability that we get such value under assumption that they are independent. So here is the large probability that they are independent. Here becomes tiny. Yeah, so the tails are very tiny. So we could so here is this evaluation from independent to 5 degrees. So the best is the using both the minimal and maximal value. Yes, because we don't know which will be the best. The best is just using both. And in comparison, the HCIC was here, the red one, so it's not very good. So from independent to 5 degrees, HCIC drop 84 times, HCR to 200,000 times. So in many tests, it seems more sensitive. Yeah. So if there are dependencies, the method is more likely to find it. Yeah. So and also much cheaper and described the from dependency. Yeah. So there is larger density here, larger here, and so on. Okay, so here is another view. So some extension of this method. So I mentioned that we have these 16 parameters which are from N01, assuming they're independent. So we can test each of them if it's independent or not. And so here are distributions of sorting 16 N01 variables and looking what is the first one, second one, third one, and so on. Yeah, so the smallest of 16 we have this distribution, second here this, and so on. So we can find analytical formulas for these distributions, and they are in the article. And so we can test each of them coefficient against its distribution. Yeah, so the first one, second, and so on, and you can this way we can get the significance level, and try to reconstruct the joint density assuming various significance levels. So So for this significant level, there is only one function in the basis. Is his second, and so we can see that the density is more likely to more closer to this one, but there is missing some noise. Yeah, so removes noise and left only strong signal. Yeah, so we can control the significant level, find the description up to some significant level. So I think it's very powerful. So we could also try to optimize the basis, yes, because we have started with this just legend polynomials. So maybe some better basis would be more appropriate. We can do it by singular value decomposition of the coefficients, getting in this basis the succeeding contributions. Yeah, so here are the values, and so again we can based on some chosen significance level we can find what is the probability that given value is significant or not. So what is distribution? So for infinite matrix, it would be Marshall-Pasteur distribution, but this is very finite matrix, like 4 by 4. So we cannot just use the Marshall-Pasteur. So it's more, but empirically you can easily find this distribution by just taking random matrices and looking at its spectrum. Singular value distribution, first, second step, and fourth. Okay, so now there is some subtle, very subtle but important correction we should include. So in HSIC, we had also these H matrices, which were these ones and minus one, and so they are tiny, but should be included. So something similar. We also have HCR, but it's completely different. So mutual information is sum of squares, and each of them is average. Yeah. So the question is how to estimate square of average. Yeah. So it's so simple. Just estimate square average and take the square. But this is wrong. Yeah. So if you take a closer look, we should to estimate square root of average. We should take the average square. You should take average square it. And then we need to subtract the variance. Yes, if you don't do it, then you get the overestimation of mutual information. So this is important correction. Very subtle, similar to this subtraction of this mean. Okay, so there are some other approaches for HSIC, like this changing the size, but I don't know. I see it looks very nice, but if I do it, I can do it for HCR because it's also kernel method. But if doing so, if using the same basis, then it's trivial, disappears. So I don't fully understand. So maybe let me skip it. Okay, so here is some slightly different, but also corrected problem. Maybe I briefly talk about it. So this is some application for shape descriptors. Yeah. So also polynomials. Yeah. So we describe density as polynomial. So one application is of molecules. So we would like to use in chemoinformatics features which don't depend on the rotation of molecules. So we cannot just put the position, put the shape there because it would have the rotation. So we need to subtract the information about the rotation. It sounds simple, but it's not. Or shape similarity metric that we can, for example, we have 3D scan, and the question is if we have separate copy which is rotated, so we could test all the rotation, but it's quite costly. Could we do it without this testing of all rotations? And yes, you can do it. So we have some invariance to rotation, and we just use it as a vector and just take some metric between these two vectors, which should it's very difficult, but it should somehow evaluate the difference between the two shapes up to rotation. Yeah, so without this costly rotation optimization. So how to do it? So we can start with the covariance matrix like PCA. Yeah, so it allows to describe approximate the shape with ellipsoid. Yeah, so to get rotation invariance, we can just take traces of powers, and it's easy to show. Well, now this is the similarity test that if all are equal, they differ only by rotation. Yeah, so we have a complete rotation modulo, complete description of shape, modular rotation, but this is very rough description, just as an ellipsoid. So we need to extend it to higher powers of polynomial. So we can do it by just taking take covariance, higher order covariance-like moments, yes, but it does not provide the description to get this decodability that we would like to maybe to get back from from these features to back to the shape. For this purpose, we can use Gaussian for the vanishing times polynomial, and we can use it to also similar way we can find it by these Hermite polynomials orthogonal basis. And we get this kind of description, so we can see that for digits we need like degree 5, 6, maybe to distinguish the digits. Yes, so and then we can calculate the rotation invariance. So they can be represented diagrammatically by this graph. So these traces of powers as the cycles, then you put your matrix in every vertex, and every edge is summation of their index. Yes, if you multiply by orthogonal matrix, then you multiply by orthogonal from one direction, by transpose from the other, and they cancel out. So it does not change with rotation. And for order 2, we know the complete set modular rotation. Yes, this traces up to a dimension, but the big question is how to find it for order 3 and higher. So again, we need to find some set of this kind of graphs. Now we have degree 3 for order 3, and again summation. So like here, so we can easily define them, but the big question is how to find a complete set of such invariants. So it's a very interesting question, I think, open still, and with many applications. So I'm looking for collaboration here. Okay, so another type of application is feature selection, that we have these two matrices, but I would like to make some projection to smaller dimension, and then to maximize the mutual information between them, for example, here. But so this sounds very costly numerically, yeah. So this all multiplication and so on, some regularization. So maybe instead, and this is linear still. So this is only linear projection, but there are often some nonlinear dependencies, so maybe let's do something better. So I think what is much better is taking these polynomials for nonlinearities on both variables to get nonlinear from both sides of the let's say, if you do it, then linear correlation and linear regression will have already nonlinearities. And we can find optimize the basis, and there is this very nice canonical correlation analysis for that we can find this direction which maximize correlation, so we can use it for this kind of basis to optimize it. So why people usually do this kind of dimensional reduction with PCA, the PCA unfortunately often amplifies noise. So it finds for the most active dimension, but they are often noise dimension. So to avoid it, I instead suggest using like this CCA to try to find direction, not which is the most noisy, but mostly correlated with what we would like to find. Yeah. So then we would like to, then they have some dimensional reduction and more sophisticated methods. I wasn't able to do it, but finally we need some neural network training and go further neural networks. Yeah. So the question is, the HSIC is used for is how to train neural networks. Like here, it could be this, that there is this one-dimensional shape, and then there is some behavior. So how to generally train such layers, and there is use backpropagation. But backpropagation is non-local, so biology cannot use it. So the question is, could you do something more biology-like? And I think that the most promising is this THB information bottleneck, that we think about the content of intermediate layers. Yeah, so we know that the input there are pixels, the output we would like to have faces. The question is what intermediate layer should contain. So this layer should have as much information as possible about the next layer. So we can optimize, like, for example, using mutual information. They also do it with HSIC. But also, it turns out it's good to remove noise information from the previous layer, to remove noise, yeah, so to find only meaningful information. So there are at least 2 articles using HSIC for that, and it would be nice to replace it with HCR. for us being much cheaper and numerically, and also global with, I think, better generalization. So I think it's valuable to go in this direction, and now I go further toward neural networks. Okay, so but before there is information bottleneck training. So there are they have these nice plots there that there are these various layers. So here is the first layer. So and here is the variable we would like to predict up to 1 bit and bits from the input. So we can see that it goes up, but then there is this strange binding that it starts going left. So the node lose information about the input. So this is this compression I have mentioned, that we should also remove noise from the previous layer to have better generalization. So this is very subtle, but so here we used 85%, he's smaller, and here you can see that the only 5% it's not sufficient, the network collapses. Okay, so a few slides now about something more subtle that usually we think about the only evaluation of mutual information or correlation, but there are usually often there's much more information there, so we could also use for analysis. For example, here is for each data that we have 2 electrodes in the same time, but here is shift slightly later, slightly earlier. Yeah, so you can see that these scatter plots are asymmetric. So this and this is essentially different. So we would like to describe it. Standard way would be using cross correlation. This is the orange plot. So we can see that it's symmetric. It doesn't see the asymmetry. So how to do it better? So instead of just focusing on one parameter, can be also mutual information. The better I think is finding that there are multiple types of dependencies. So also in higher moments. So we can for each delay, like 1,000 of them, you can model the joint distribution of polynomial and find the dominant contributions with PCA, seeing that usually there is change in this and it behaves like this. So it's similar to correlation, this first feature, but it's it's more localized. So it's better to find synchronization than just correlation. Then next features show there is asymmetry. We can practically work with it. But the best application I think is for Granger causality of these kind of approaches. So in Granger causality, we have one-time series and second one. And the question is if the second allows to, if you would like to predict from the first from its past, if you add the second, can we improve the prediction? If yes, then it's said there is Granger cost. But the problem is, for example, there could be a common cause. That there could be some area event which causes both. Yeah, so that's a difficult question to distinguish. But the method I presented seemed to be able, at least sometimes, to do it, distinguish them. So there are these 2 types of improvements. So one is also trying to find what is the propagation time between, let's say, these two parts of the cortex. So we can find the residue as value minus its prediction from its past, and then find the correlation between this residue and the second sequence shifted by some various data team. And the maximal correlation for the data team is the propagation time, average at least, yes. So this is one simple extension of Granger, but you can also have the second one using this kind of various type of contributions to joint distribution. So it needs better normalization, that instead of just subtracting the value, like expected value, we need to predict the type probability distribution and go to the cumulative distribution function. If you do it perfectly, then you need to have this IID independent completely sequence. In practice, you can do it, but generally we try to remove information about the past from this sequence. So then we can check if there is still dependence with the second sequence. Yeah. So as for Granger. So we have later this well normalized and earlier this just normalized and find this various types of contributions to joint distribution. This way, for EEG, for example, the blue one is maximum after 100 milliseconds, so like direct communication. The orange one has 200 milliseconds usually, so maybe it's indirect communication, then you went out and go back. And the third one, the green one, often has maximum in zero. Yeah, so type of dependency which has maximum zero can be only common cause. Yeah, so there needed to be something earlier which caused both to have zero propagation, some let's say visual stimuli. So it seems to be able to distinguish common cause. Yeah, so this way. So I think it's very nice to help you this impossible task. So we have also used very similar approach for different applications. For example, there can be used Fourier analysis further. And so here is state of art for some bearing analysis, and here is ours. So we can see that the the noise is much lower, and moreover, we have various types of spectra, which can be imagined is that it describes various types of this device we are describing, like bearing here. Yeah, so each, let's say, balls and the rating has different spectra, so hopefully they correspond to these various parts. Also, we can do it for financial data. So, for example, here is now this evolution of moments. So, standard is DCC, that evolution of correction coefficient between markets, for example, here. And here is the better looking at the joint distribution and the main contributions. So instead of one, now we have like 7 complementing parameters, and we can check versus some important historical data like Lehman Brothers collapse 2009. So I think the second one. So the question is and we can check if these C's or not, this feature, and having 7 complementary, probably we see it, and we can see that indeed that it doesn't see many, but if you look at those, they should see so can better describe dependencies between the markets. Okay, so as the last part, I have more about these neural networks based on HCR, so development, like information bottleneck. So the current artificial neural networks are still inferior to biological, and there is this nice experiment that they just put 1 million biological neurons, and they learn to play Pong, and they were much better than based on standard based on these computers reinforcement learning. Yeah, so there are some qualitative differences and between them, and the question is how to do it better. So here are the classical architectures, this multilayer perceptron, or now these popular Kolmogorov-Arnold networks, that we have some concrete parameterization and we have one directional propagation. So, but let's think about the real biological neurons are essentially better. So the question is what was hidden in kind of very complicated structure. So let's think about the differences of single neurons. So there are spiking approaches, but I'm not very optimistic about them because it's too complicated. Yeah. So here we have both them. There is annihilation of spikes if they meet. There is propagation in both directions, while those only have one direction propagation. So instead, we should think about some logical neuron, something slightly better than those. Yeah. So add missing properties to those from biological neural networks. And so what are these properties from mathematical perspective? So one, as mentioned, it is this that if you have axon, there's propagation left and right. So we have fundamentally bidirectional propagation, and if so probably evolution was able to exploit it for some training inference. So we should have this, I think, to be able to do two-directional propagation. Second difference is that we usually work on values, but for example, rats also choose make decision based on variance. Yeah, so maybe they somehow work on probability distribution. So maybe not only values, but also higher moments, for example. So how to do it? And the third difference is that backpropagation is said to be not local, so not biologically possible. So in some different methods, like this information bottleneck I have mentioned, yes, that only communicating only with neighboring layers, maximizing information, mutual information in the next one, minimizing the previous one, and so on. So how to get all these three properties? So more biologically logical neurons. So we can use neuron which with this model of joint distribution as polynomial here. This way we can just substitute some variables to getting constraint distribution and on values. So let's think about these examples. So based on these points, we have fitted the polynomial and having as the joint density. Having it, we can, for example, substitute one variable and getting conditional distribution in one direction, or the opposite and getting the opposite, or take the expected value, then we get like plots like here. Yeah, so here is the expected value of y under condition of x, or here's the opposite if trying to propagate the other direction. Yes, so it naturally can both, so such neuron containing joint distribution model can naturally both work on probability distributions and change propagation direction. Yeah, so like biological. So I think this is more biological. We can also use this information bottleneck, like so they also work on probability distribution. So I think this approach is very biology-like. Here is in 3 dimensions. So similarly, and here are the formulas for 2 dimensions. So the parameterization is very simple. This joint density is just this linear combination of these parameters. We can estimate that directly, or use substitute one variable and normalize to get conditional density one direction, or take expected value to get value propagation, or we can change the direction of propagation. Yeah, so we get the missing properties of biological neurons. And this is very cheap numerically, just matrix multiplication. Yeah, so maybe this kind of the question is what mathematics is hidden here. Maybe some matrix multiplication, very simple one, obviously. Also, having these parameters, we have models of they are moments that we can easily evaluate the amount of information propagation, also for like mutual information, for information bottleneck training. Yes, also we have very nice control of the behavior. So here is the derived this propagation, and we can see that restricting only to pairwise dependencies, so only between pairs of variables, we get literally trained of two-part polynomials, which is CAN probably. So this is extension of CAN. You can see it this way, and you can gradually improve or extend over CAN in steps. And we made this article, which is practically CAN. So yes, the legend CAN. So the only thing we have improved was instead of standard normalization as rescaling, replies to these quantiles, these EDFs, EDFs, CCDF. So why is better? So now we can see here is the training. So we can see that the best is just degree 4 and using this better normalization, because this now we can see that the low degree polynomial like 4 is much better for representing these points than here. Yeah, so why for high degree the better is maybe it's worse, but here we have overfitting. But to have a generalization, you should use small models, for which purpose it's better to use low degrees and this better normalization. Another simple example is just one neuron for similar as CAN application, that we have some function, we like to get it from size, let's say 1000 sample. So here we literally model joint distribution as 5-dimensional cube. Yes, the entire estimation is this direct estimation is just a product, and it reconstructed the functions slightly deformed because we have this normalization, but basically at this simple case it works. So here instead of predicting values, we can also predict probability distribution. So for this purpose, we need to separate the model at the moments, and then we can combine them into polynomials, getting the probability distribution. So we can easily also we can both propagate the density, but we can also in final layer we could just transform prediction of values into prediction of probability distribution by separately predicting moments and finally combining them into the density vacuum. So here are some advantages of working with probability distributions, starting with having uncertainty. Or, for example, here is this bimodal distribution. If you have a value prediction, then you can point here what makes no sense. If working probability distribution, you can see it. You can have evolution of probability distribution like here. There are many advantages for various applications. Okay, so we can also propagate densities. So it is so this way we treat density as a vector of moments. Yes, vector having expected value, variance, skewness, kurtosis, let's say, and we propagate such vector through our networks and finally get also such vector of such form moments as prediction. Yes, so we can relatively easily transform network working on values into network working on probability distribution. Both directly propagating them, but also finally just predicting a few moments and getting probability distribution. Okay, so also this nice approach, at least mathematically, I don't know if practical, but if you have this joint density, let's say of 5 variables, 4 inputs and 1 output, we could try to automatically approximate it as this tensor decomposition, this extension of singular value decomposition. So let's say try to approximate it as with these 3 smaller tensors for this formula. So in theory, we could train it this way, but I'm not sure if it's very practical. You can skip it. So here some training, and here is the last slide. So this approach based on HCR can be seen as extension of CAN, Kolmogorov Arnold networks, with many advantages. So we can just take some single steps. So for example, you can such train CAN can be changed into propagation in the second direction. We can work on probability distribution, not only values. The interpretation, the parameters are moments, so we know what they mean. We can add higher dependencies, so CAN is only for pairwise dependencies. So we have evaluation mutual information, very inexpensive, so we can control, monitor the information flow and, for example, use for training. And there are many additional training approaches like direct estimation, like this tensor decomposition and information bottleneck, I think very nice for biological neurons. So thank you for attention.